code as well. The channel code can transform some values to other values, and then I can make it lower energy if I want to. Okay. So I'll choose the channel code to be not just lower energy, but also to minimize the effect of noise. Okay, so here I'm just reinforcing the concept that the sum of the squares is the energy. We can compute the energy of the source signal, we can compute the energy of the channel signal, which are independent, different from each other, because you have two choices to intervene. You can choose the source code, you can also choose the channel code. Okay. And I think what I was telling Alan was that Alan said basically, yeah, you choose the source code to minimize the redundancy here. Yeah.
So I was confused whether the decimal value of the binary digits has got any relevance to the amplitude.
So for this particular sequence, yes, we are looking at the amplitude over here. We're choosing these to be amplitudes over here, yeah. Because of this thing right here, right? We're talking, think of these points being in there. Okay. All right, let me move on to the, right. So if you have this particular observation which says that if I increase the signal amplitude, I can get rid of noise, then why bother with having noise? You know, we can just boost up the signal level so high, we're never going to have to worry about noise ever again, right? We just keep boosting it up. And there are two reasons why we don't want to do this. The first thing is that each value over here, sigma x, is going to result in energy xi square. Right? Each xi over here that I'm sending, if you're sending at 5 volts, and if I went to 15 volts, actually the energy goes up a lot more. So to transmit that bit on a wireless channel, for example, is going to drain my battery. Okay, I'm going to spend more energy out, right? So if you have some ambient noise in the wireless channel, it's going to be the same thing. Same thing for a wired channel, right? If I'm going to send stuff on a wired channel, I'm going to basically send these voltages, and that's going to cause more energy to be used up. And so I don't want to waste my energy if I don't have to. So, okay, I'd rather do something which is good enough. That's the first reason. The second reason has to do with wireless channels, where if I have a wireless receiver, okay, I have a wireless antenna on some receiver, and I have some transmitter T1 and transmitter T2. If this one is blasting away with very large amplitude, and this is having small amplitude, what happens is that even this is further away, it's going to cause interference at the receiver. Interference always at the receiver, and what's going to happen is the receiver is not going to be able to decipher things. So for the sake of argument, imagine that you have a cell phone and you're making a call, and as you're calling somebody in, say, Toronto has this enormous cell phone, the size of this room, and they're blasting away on the same frequency at very high power. Well, that's still going to cause interference to you. Okay, because even though, so they're going to get a very, very good signal to their recipient, okay, but you're going to be hurt. In the limit, if you have a particular frequency band, and you have even one transmitter of infinite power anywhere in the universe, if they transmit, everybody in the universe, everybody else in the universe receiving on the channel is going to get affected, which is probably not a good thing, okay. So we want to restrict the signal power, signal energy, in order to prevent interference at the recipient. Okay, so that's what we do. So there's two reasons to restrict it. So we're not going to transmit at infinite power at all. So I should add that power and energy in electrical engineering are very specific terms. Okay, if you remember, power is your instantaneous value, energy is power integrated over time. Unfortunately, in information theory, they confuse the terms. So I think, Raymond, you're going to be like, how can you say that? So yes, they use power and energy interchangeably, which is wrong. But anyway, yeah.
So how does so what if you have transitions as symbols for transmitting the signal rather than having voltage levels for symbols?
Right. So if you're using transitions as opposed to, it's still, we have to choose the voltage levels where you're going to transition to and from. Okay, what we're looking at essentially is the effect of noise on the transitions, right? So phase noise is going to cause distortion of the phase.
So is that any lesser than level noise?
So generally speaking, the phase noise is going to be, or frequency noise is going to be less than level noise, right? So that's why AM is noisier than FM. FM is noisier than phase modulation, which is what's used for cell phone transmission, right? So we don't use FM analog, we use digital, and once you go into OFDM, then you get even better, because these physical processes don't generate phase noise. Yeah, so we don't have that problem.
Probably some like Ethernet, or like what we use is some sort of transition based?
That's correct. So yeah, we use Manchester encoding for Ethernet, or if you also use called 4B, 5B encoding, the different kinds of encodings that are used at the yes, and those use transitions. There's another reason for using transitions, which you want to equalize the number of zeros and ones, because of otherwise you have other problems in the transmission systems. Okay, but yes, if we choose signal values which are relatively insensitive to noise, then you can reduce the signal power, which is always something we try to do. Okay, so let's move on to the capacity of a Gaussian channel. And there's a little bit of math here. I'm going to walk you through it. It's not as complicated as it seems at first glance. And let me first explain to you what's going on. So last time we studied this notion, and I drew this picture where we had these on the here were the x, the signal values, and we said that the effect of the channel was to map each point into a set. Okay, and we said that the h of x was the entropy of this system over here, and this set had approximately 2 to the h of y given x. Okay, n y given x, where n, we had n symbols, values in here. So, and then what we were trying to do was to separate out these sets one from the other, so that when we got anything in this range, we could figure out that it corresponded to this signal. Okay, that was the intuitive reasoning behind Shannon's theorem, right? How do we essentially separate out the sets of received values so that we can work backwards and figure out what is being sent almost surely? Okay, it's always almost surely, but never for sure. We're going to use the same exact reasoning over here by using these results from hypergeometry. Okay, so how do we do this? We start with this observation, okay, that if I take a sequence of n values, x1 to xn, okay, then the energy is going to be sigma xi square. That's the first thing. And this corresponds to a point on the surface of a hypersphere. Okay, it's almost surely a point on the surface of a hypersphere. It's not guaranteed, but it's almost surely as n tends to infinity. So I'll just put as just to emphasize that it's almost surely. Okay. What you're going to do is to add two things to it. One is we're going to add W, which is the signal, okay, the signal bandwidth. And if you remember, that's sort of, if you take the Fourier transform, it's basically band limited by W. So all the frequency components lie inside W. Okay. So that's why we need to understand a little bit of Fourier domain, transform domain, to understand information theory as well. So I say that the transform of this in the Fourier domain, but I have omega over here, and I have the amplitude over here, is going to be band limited by W. So if I do this, then I basically can show you can see that we need to go into, if you have if you're going to have the signal sent on the time t, okay, I have these signal values going to add sent in time capital T. So T is the duration over which these signal values are sent. Then basically we can see that you need to have 2Wt should be the number of signals to be sent, okay, for us to completely capture the signal over here. So in other words, we want n to be equal to, greater than or equal to actually 2Wt, okay. Otherwise we don't have enough samples. Okay, this is sort of the sampling theorem. We ignore the 2 pi for now. This is all we care about, okay. So if the bandwidth is certain value, then I need to have at least this. And you see the dimensions match our t's in time, w is in hertz per second, s inverse. So these two cancel out, so you get a pure number, and that's a number that we want. We want to have at least that many. And we'll just take the limiting case, which is n equals 2Wt. So this means that our signal n, this n over here, is this n over here. We need to have 2Wt signals being sent in time t. Okay? Any questions about this? Okay. So somebody says my signal is limited by 20 hertz. then I'm going to say, okay, then W is 20 hertz. Then in time t, I'm going to send you so many signals. Okay? Because per second, I need to send you 40 signals. So I'm going to send you in time t, it's 100 seconds. I need to have 40 times 100 signals. That's how many signals I need to send you. That's a block over there. Okay, so we haven't said anything about power yet. And so I'm going to say that let's assume, or let's denote the average energy per signal and that's going to be nothing more than sigma I xi square by n, and we'll denote that to be P, right? And so what is the energy associated with this 2Wt? It's going to be energy of the block is going to be 2Wt times P. Okay. All right. So this is a point on the surface of a hypersphere, right? And the energy is going to be 2Wtp. Okay. So since it's on the surface of the hypersphere, okay, and we also need to know the distance of this point from the origin, right? The distance of this point from origin is just going to be the square root of sigma xi squared. That's Euclidean distance. So the radius okay is approximately equal to square root of 2Wtp. Okay. All right, so let me go with this once more because I think I lost you. So I'm taking a set of signals, n signals, x1 to xn, where each signal is some value like 0, 0, 0, 0, 1, 0, whatever. I don't really care. N signals are sent in time t. Okay, so that's what I have. These signals have an energy of sigma xi square. Okay, that's what we said. And we'll denote this to be equal to Pn, okay? So because the average energy is going to be 1 over n, so signal n times p is going to be the energy of this corresponding to over here. And I'm saying that n over here, if it's going to be sampling fast enough, the signal which is the analog signal which is of bandwidth w, n must be 2Wt at least. So we'll say n is equal to 2Wt. Okay, in which case the energy is going to be 2Wt times p, because it's np, it's 2Wtp. Okay, and we know that the signal point is almost surely on the surface of a hypersphere because I wrote that over here. Energy volume of a n-dimensional, consequently almost all points are on the surface. So this point, which is x1, xn, that's also an n-dimensional point, must be on the surface. If it's on the surface, what's the radius? Well, the radius is going to be the square root of this, because this is basically sigma xi squared. It's a point on the surface, right? So the distance of this point from 0 is the radius, and that's nothing more than 1 over is going to be square root of sigma xi squared. So the radius. So energy is this r, and I should just add r equals square root of sigma xi square, right? Because okay, so we're kind of getting this funny thing that I take any point, its average signal. If I take any point, it's on the surface. So if I take the square root of the energy associated with that point, I'm getting the radius from it approximately. Okay, and that tells us the radius of the hypersphere, okay, over here. Okay, so everybody on board with this one? Because if you agree to this, everything else is trivial. Okay, this is the part where we've kind of taken 3 or 4 different facts and then stuck them together. One fact we have is that a signal corresponds to a point. The second fact is that the point is almost surely on the surface of the hypersphere. The third point is that if you're on the surface of the hypersphere, okay, then the radius is going to be the square root of the sum of the square geometrically, which also happens to be the square root of the energy, okay, by definition of energy. The other fact is that the number of points is coming from the sampling of the signal. So you're going to have basically 2W points being sent in time t. And so if the average energy of each signal is p, then 2WTP must be the total energy, and we can relate that back to the radius of the hypersphere. So we've kind of taken facts from basically hypergeometry and some facts from signals and systems and some definition that I have right here to come up with this rather interesting conclusion that a point which if I have a signal which is an analog signal of band W, then each set of underlying channel signals that are needed to represent it is going to be on the radius of a hypersphere of this radius. Okay, so it's a lot of small parts, but each step by itself is hopefully obvious. It's just when you put them all together, you get a rather surprising conclusion. Okay. Any questions about this? Okay. I am making the assumption that the signals are IID. Okay. I need to make sure that they're IID, otherwise I won't get this result. But as long as they're IID, you do have this result over here. So I'm going to put this up. Everything I've said is actually in the text, and I'm going to request you to go back and read through that one more time, because it's easy to read it. It's much harder to figure out what's going on. Okay, but that's what's going on over here. Can I move on? Any questions? Yes.
So you have the radius of hypersphere in terms of p.
That's correct. And in terms of W, T, and P, yeah.
But p is sigma xi squared by n.
Yes.
So if you know p and you know n, then you know the radius already.
Well, n comes from WT, yes, correct. If you know P and N, you know the radius already, that's correct. Yeah, but I'm relating N to W and T from the Nyquist sampling theorem. You're right, if I know P and N, sure. Energy is Pn, right there. So I know the radius is going to be square root of Np. I'm just substituting 2WT for N. Okay, so using the same exact reasoning, okay, if I have a series of noise values, let's call them N1. Sorry, I don't want to call them N. So what did I use over here? I didn't even put this. Let's say the noise, I don't want to use N for that. Let me just call it epsilon. So I have epsilon 1, epsilon 2, all the way up to epsilon N. Okay? And the average noise power, noise energy, I guess, is going to be sigma epsilon I square by N, and I'm going to denote this by capital N. Then I can say that the noise viewed as a signal, is going to be on a radius of a hypersphere as well. It's going to be this particular point, okay, is going to be on a surface of a hypersphere okay, of radius, so almost surely it's going to be a surface of radius square root of 2WNT. Now why do we get the 2WNT? Because if I have n values of the signal, each one of them has an associated noise value. I'm not getting this n because I'm trying to code anything at all. I'm just sending n values, 2WT values. Each of them has a noise, so I'm getting 2WT from there, and the average power is n. So average energy is n, so I get this being the sigma epsilon I square, and then I take the square root, that's the radius. Okay? So far so good? Okay, so now the theorem more or less just drops out of these two values, because what I'm going to try and do is to separate out the signals far enough. Okay, so let me go back to that simple picture over here that I had, where I had said I had these 4 keying values and the noise was going to distort them. Okay, I want to kind of make sure that these are separated out far enough in space so that even if noise were to move these out anywhere else, the closest valid signal point is going to be well known. There's no overlap, or I should say almost surely there's no overlap. Okay, we're always going to do everything almost surely because we can't do it for sure. It's going to be almost surely. Okay. How do we do this? Well, the signal can be used as a sort of a hypersphere. Okay, all the values of the signal that you could possibly have are points in the surface of this hypersphere. All the noise values are going to be surfaces or on the surface of a smaller hypersphere, which has a small n. Hopefully n is less than p, otherwise we're in big trouble. Okay, if the noise energy is about the same as the signal energy, then we really can't do anything at all. So we won't have n less than p, so it's going to be a smaller sphere. So when we take the additive aspect of the noise, then we have a signal which is p plus n. Okay, that's going to be the average energy. So this corresponds to hypersphere of size square root of 2wt p plus n. So all the received signal values, remember we're not talking about what is transmitted, the received signal values are going to be on the surface of a sphere with this radius, square root of 2wt p plus n. Okay? Now, let's draw that. So I'm going to reuse this and say, okay, the radius of the received signal value is square root of 2wt p plus n because it's additive noise. That's the radius of the sphere. Okay? How did Shannon prove his theorem? He said, okay, I'm going to have 2 to the hy, approximately the size of the received values. Here we've kind of quantified that as being a hypersphere of this size. And I want to choose the number or restrict the number of signal values so that after distortion, they're still distinct. They're not overlapping almost surely. Okay, so it becomes a packing problem. I'm going to have a bunch of these smaller spheres, hyperspheres over here. Each of these guys has a radius of square root of 2wt n as the radius. And I want to basically see if I can put each signal point as the center of these little hyperspheres like this. What's going to happen is it's going to get distorted, but I can still find out where it is. So if the distortion results in something like this, I still know it was part of this hypersphere. As long as all these orange crosses result in non-overlapping almost surely, right? As long as the orange crosses never go into another one almost surely, we're in good shape because we can say, oh yeah, that one, well, it really belongs over there. Okay? If we can do that, then we're in good shape. Then almost surely we can decode. What I mean by almost surely we can decode is that we can actually figure out what was being sent to the signal point despite there being noise. Okay? And so for doing this, what we need to have is we have to restrict the total number of signal points, okay, to be smaller than this ratio. Okay? Because the volume is this, and this is the volume over here. So as long as this ratio is the number of signal points is less than this, we're basically going to be fine. Okay, why? Because radius of r means the volume is the r to the n. So that's the volume of this big sphere. That's the volume of the little sphere. And I have one signal point corresponding to each little noise sphere. So number of signals, so this is greater than or equal to number of signals sent in time t. You have to remember it's in time capital T. Okay? So this, if we just cancel things out, so this number of signals sent in time t is less than or equal to, so this one is going to be less than or equal to 1 plus p over n to the power wt, because n is actually nothing more than 2wt. Okay, so if you simplify this, it turns out to be just just this over here. Okay, 1 plus t to the n wt. Okay. Because we can take this whole thing raised to the n like this, okay, and then the square roots become n over 2, and then that 2wt cancels the 2 over here, and then wt goes away, so you just get 1 plus p over n. It's a really simple, straightforward simplification. Okay?
So what is less than equal to?
Beg your pardon? Oh, this, okay, maybe I should rewrite this. So, number of signals sent in time t is less than equal to p. This is what I want, so I'm going to erase this because that's confusing. There. So that box is what I want. Okay, I'm going to take a break, and then this then tells us this actually is pretty much the theorem now that I want. Okay. Yes?
Yes, smaller circles, that's the one signal but with noise.
One signal block. One signal block
With noise.
with noise.
Noise, that n is, capital N is the average signal.
Average noise per signal element, yeah.
But that's average.
That's average, correct. So the total noise is n times that much, because we're taking if you take n signals, then the total noise is going to be 2wnt.
But there will be other noise, specific noise that's larger than that average.
Yes, so if n is long enough, almost surely the noise energy is going to be this, 2wnt. Okay. Again, there's a law, the asymptotic equipartition property tells us that if you take long enough things, everything looks typical. So yes, you're right. It could be that specific noise values could be greater, but almost surely, so everything is almost surely, everything is typical. Okay, we always deal only with typical things over here. So law of large numbers helps us by saying that, yeah, the average is what's going to affect the noise.
Actually, I mean,
Where are we here? Okay, so I want to now finish the last little bit on this capacity theorem, because all we need now is this observation that we had earlier, that if I can send, so let's just focus on this. So the equation 9 in the text basically said this: information rate of a channel, and this is more or less by definition is less than or equal to log base 2 of the number of distinct messages per second. We sort of defined that to be the information rate of a channel. How did we define this? We said, well, if I have symbols, I can have k different symbols, then I can have log k is the information rate, right? If I have 4 different symbols, then I have my information rate is 2 bits per second. Okay, so how many different signals can I send? If I view these as being messages, how many can I send? Well, 1 plus p over n in time wt. So in 1 second, I can send 1 plus p over n to power w, right? In 1 second, because I had t in t seconds. And which implies that the information rate, which is the capacity of the channel, is going to be w log 1 plus p over n. Okay? And that's the information rate of the Gaussian channel. And I should say, almost surely. Okay, everything is almost surely. Okay. This is a very, very good result, because all we have here is w, which is the width of the signal, which I drew up there, the energy of the signal and the energy of the noise. Okay. Now we can convert the energy into power. Okay, we can convert the energy into power by saying that, I'm going backwards over here. Maybe I should go start it. Yeah, I'm going to stay. Yeah, actually, I don't need this here. So if I have a signal that looks like this, okay, the energy is the area under this curve. That's really what the energy is, okay? If I have a signal of duration or thing of duration t, the average energy is going to be what? It's going to be the average area under this curve, okay? However, I can also view this as being the average, this average multiplied by the duration. So in other words, I can always find I can sort of define the average, obviously, to be this average value multiplied by the duration is the average energy. Okay, so the average energy and the average power are the same. Why? Because the time is fixed, right? So if I tell you the average energy is so many joules, then the average power is the corresponding watts, right? So I can now go from energy back into power. So P by N is also going to be, so P by N, which was ratio of energies, is also equal to ratio of powers, average powers. So the point I want to make here is that we are not talking about the specific power of a average of a particular signal, but the average power of a signal. So it doesn't really matter that 0, 0, 0, 0, 1, 0, whatever. I'm just looking at the average power over sufficiently long over the period of time t. That's a well-defined quantity, and so that's P by N. So now I've gone from energy to power. The first thing I've done. The second thing I'm going to do is to reinterpret W. Okay, so for this information rate, this was energy over energy, so that's now power over power. Fine, the ratio remains the same. W was the width of the analog signal, the channel width of the analog signal. I'm going to reinterpret that. I'm going to say that the channel has a particular bandwidth. It's it is the width of how much in the frequency domain, what kind of signals can go through. So, and I'm going to appeal back to what I said in the beginning. I said, okay, if I have a auditory signal, okay, the ear cannot hear more than 40 kilohertz. That's the bandwidth of the ear, roughly 20 to 20,000 hertz. In some people, 40,000 hertz. So the ear has a bandwidth. If the signal has a higher frequency range than that, it doesn't really matter. All I care about is what is it that the channel can carry. Okay, so I'm going to reinterpret W, which I initially said is the width of the channel of the signal, as being instead the width of the channel. In other words, this is the most the channel can possibly do. I can't do any better than that. Okay. Then we can say that the information rate is the maximum rate at which we can carry messages on a channel with width W hertz. Okay, the channel is going to be W hertz, then the maximum information rate of that channel is going to be no more than this. Okay, and by this change in perspective doesn't change the math, because all I'm going to now say is that I'm going to sample the signal. Okay, the signal may have some intrinsically larger value over here, and then I'm going to sample only, so this is omega regime, I'm going to sample just W of it. If by doing so I may be losing certain parts of the signal, fine. Okay, I'm losing it, I'm going to have aliasing, all those problems arise. Nevertheless, this is all the channel can actually carry. Okay, and so this becomes the information rate of the channel. Okay, and so this change in perspective is quite subtle, and I'm not doing it much justice by presenting it in this way, but to do more requires a lot more effort, and intuitively I'm just going to sort of wave my hands and say, look, I started out by saying that's the signal band. Instead, I'm now going to say it's a channel band, and everything works, and you're going to have to more or less, the math does go through, but I'm ignoring certain subtle aspects. They're not crucial, but they're subtle. I'm going to leave that out. Okay, which means that now we have a really powerful thing. If somebody tells me I have a channel of bandwidth 10 megahertz, and I tell you the signal power and the noise power, I can tell you what the information rate in bits is. Okay, so to demonstrate this, let's look at the homework example where I said, what is the channel capacity of a Gaussian channel with bandwidth of 10 megahertz and with the signal to noise ratio in dB of 10 dB and 30 dB and 40 dB. So the way we interpret SNR in dB is like this. We first divide by 10 and then we raise 10 to that power. So 10 dB, we divide by 10, that's going to be 1. And then we raise 10 to the 1 is equal to 10. And 40 dB, we divide by 10, we raise 10 to the power, that's 10,000. Okay? So in the first case with 10 dB, the signal has 10 times the power of the noise. In the second case, the signal is 10,000 times as, on average, 10,000 times as powerful as the noise. So 40 dB is a lot. Okay? 10 dB is only 10 times. What is the corresponding information rate? Well, we can just plug it in over here to say that the information rate is equal to 10 megahertz is 10 to the 6 times log of, in the first case, 1 plus 10, which is going to be 33.2 megabits per second. In the second case, information rate is going to turn out, using a similar computation, to be 152.8 megabits per second. Okay? So this is really nice. Okay? I can go from this very abstract hyperspheres and things like that to something that you use in practice today. So if I tell you Wi-Fi 802.11 uses 22 megahertz band, which is what it is, then I know that this W is 22 into 10 to the power 6. Then I can immediately tell you for different values of signal to noise ratio, which is this in dB, what the corresponding number of bits per second is going to be, and that's what we use all the time. Yeah?
I got slightly different values. I think it's log base 2 versus 10 to 7. Yeah, I got 34.6.
My calculator is very old.
Okay.
What is it, 34.6?
Yeah, I think so.
34.5. Okay.
The other one is 132.9.
Really? I really better get it better. Okay.
I think you did log natural.
No, I just did log natural divided by log E in this. It's okay. So what you do is you just divide by, I did do log base 2. Yeah. Yeah.
W is 10 megahertz. So
Right.
You should write 10 to 7.
Oh, I'm sorry, 10 to the 7, yeah, 10 into 10 to 7, sorry. Yeah. But this answer is correct, yeah. Sorry. Okay, so I have one last thing to say, I think, which is that the way that people talk about bandwidth in computer networking is terrible, it's wrong. Please never make that mistake if you can. And my explanation for why that's the case is in there, but I don't want to go over it. Okay, so no class on Monday, and exam is on Wednesday, and good luck with it. And if you have any questions, put it on Piazza. I'll answer it as soon as I can.
Location?
Yeah, the location is on Piazza. I don't remember anymore.
Is it still open book?
Open book, open notes, open brain, you know. So I hope you liked the class. I enjoyed teaching it. Thanks for sitting in, attending, and sorry for all the mistakes. But okay, I'll see you in the exam. Thank you.